Alright, so this video is going to be a very short video because I have class and I'm going to have to stop recording the videos. So again, I just wanted to summarize this again. So water breaks the trend, usually as the molecule gets bigger, and these are getting bigger because S is bigger than, SE is bigger than SE and TE is bigger than S. The boiling point increases because they have stronger London dispersion forces. Because remember, bigger molecules have stronger London dispersion forces. And that trend also holds true here. As the atoms get bigger, the boiling point gets higher because there's stronger London dispersion forces. But water breaks the trend because it can hydrogen bond, and a hydrogen bond is a much stronger than London dispersion forces. So the next two slides we're going to work on identifying what intermolecular forces molecules have. So this molecule is a polar molecule, right? So it has a dipole moment that points in this direction. So it does have, all polar molecules have dipole forces, and every single molecule in the world has London dispersion forces, except for ionic compounds, okay? However, it does not have hydrogen bonding, because it does not have N or F. It also doesn't have hydrogen attract to a very electronegative element. But the point here, okay, and I want you to take pictures of the slide and write down the point, okay, the point here, okay, is that all molecules, no matter what, have London dispersion. And if all polar molecules have dipole. So every single molecule has London dispersion, okay, but only polar molecules have dipole. And then there's a special type of dipole, which we just went through, called hydrogen bonding, that only some molecules have. So here it says, and I drew them for you to save some time. So which of the following exhibits dipole as well as London dispersions between the molecules? So they all have London dispersion. Every single molecule has London dispersion. Okay? So now we need to know which ones are polar or nonpolar. This molecule is nonpolar because it's symmetrical. Okay, this is actually square planar. This molecule is also nonpolar, so it's symmetrical. This carbon has 2 electron domains, so it's also sp hybridized. Now this molecule, people get confused, is also nonpolar. If you look, these dipole moments are going to cancel here. And then these are all in one plane, so it's like a trigonal planar molecule. So all those dipole molecule enter. So these 3 molecules, which I'll circle in blue, are nonpolar. Okay? Because they're symmetrical. And they only have London dispersion forces. I believe this one would have the strongest London dispersion forces because Xe is a huge atom. So it's like compared to P and Cl, Xe is huge. So since this is the biggest one, it would probably have the strongest London dispersion forces. This one down here is the only molecule that's polar. It has a dipole moment that points in this direction. So this one would have both London dispersion and dipole forces. So the answer to this question would be this one. This is the only one here that exhibits both dipole and London dispersion forces. And I would like you to also take a picture of the slide. So that is the end of this video. Obviously this one was a short one. The next video is going to look at properties that are affected by strengths of intermolecular forces. So we are going to look at melting and boiling point. We are going to look at energy required to make a phase change. So if you're at the melting point, how much heat do you need to add to make it turn completely to a liquid or completely to a gas? We're also going to look at factors that affect specific heat capacity. If you remember the formula, Q equals MC change in T. And that's what I wanted you to write in that spot here. So in that spot, which I don't have my pen out, so here, you needed to write Q equals MC change in T. That's a formula that we used a lot. Intermolecular forces determine specific heat capacity. And last but not least, we're going to look at vapor pressure, and we will define that again, because we did talk about vapor pressure earlier, but we will define it again in the next video. So the next video is going to go on how intermolecular forces affect these properties, and hint, hint, it has to do with the strength of the intermolecular forces.